Okay, so we should still be expecting 30 more students. Okay, so we'll be beginning maybe in 3 minutes. Okay, I think most of the students are here. Maybe next time we'll take attendance at the beginning. Okay, so yeah, if like 5 minutes since the course begin, we should take attendance and make sure we will not have to start late. Yeah, okay, so last time we talked about the networking, right? So networking layer, and today we'll continue, okay? So because the purpose of networking layer is really for routing, right? So, I might not upload the slide yet. I will do the update by today. Okay, so if it's not there already, I will upload the slides and I will also upload the video. Okay, so you should get it by today. Okay, and yeah, for the midterm, we will get the marking done by this week, and you are expect to see the results. Okay, right. So let's begin. So if you remember, we have covered two set of slides. Okay, one is about IP datagram, right? So format. Another slide is about IPv6 and how to do tunneling, right? And so, but these are just the IP packets, right? The IP datagram. And the important thing is that the IP datagram should be flowing in the routers and get sent from the source to the destination, right? So, and there needs to be protocols for doing that, right? So, and one important thing is for routing is how to find the routes, right? So we have so many routers. Which route should a packet, right? So a datagram take, right? So this is what we will be covering from now on. Okay, we will have, I think, 3 slides on this. Okay. So again, a recap, we're at the network layer, okay? And the functionality is to set up routes within a single network, right? So basically, we want you to be able to route between each other, right? And by routers. And the key challenger here is that, it's a, the routes are basically, you have so many routers. It's a distributed environment. and how do you update it? I say some routers are gone and the other parts are newly joined, right? And some places are unreachable. How can we dynamically update it while every router is kind of autonomous, right? So how can we do this, okay? Another thing is that, let's say if you have some updates to the network topology, that some routers are added, for example. Maybe we will have a shorter path, or maybe the older path is gone, so we have to take a longer path, right? So how long does it take to propagate those updates, right? So this is called a convergence time, okay? Then how long it takes for us to reach a route that is stable, okay, after an update. And finally, we want to avoid the loops, right? So because if you think about it, if there's a loop, right, so then the packet will never be eliminated, right? So there will be more and more packets in the network. Okay, this is what we want to avoid. So in this control plane, we have two protocols called RIP, okay, and OSPF. These two protocols are what we will be covering today, okay. And this is actually for routing within your institution. Okay, we will see that. So, okay, and BGP is for routing across different institutions. Okay, let's say for UAB, we probably are just using one of these two, right? Probably OSPF. Okay, but now if you want to route from UAB to MIT, for example, we are using BGP to find a route. Okay. So so you can see we have two levels. Right? So this is the institution level, this is cross institution. Okay. So the internet routing is actually organized as this kind of two-level hierarchy. Okay. The first level is called the autonomous system. Right. So it's each like this OSPF, like RIP, they are configured by the institution, let's say UAB by itself. Okay. So this is called autonomous systems, AS version. When we talk about AS, we mean this autonomous system, like your own network. Right? So this is a region of network and a single administrative domain. Okay, like UAB, we have so many machines, you cannot just use switch, right? Switch is like your lab room, okay? Or with like office within a building, even just a story, right? So, and if you wanna, if you wanna, even for a building, probably already need a router, right? So you want to route across the entire UAB, okay? Then UAB need to have IT person to set up those protocols, those hardware, those routers, and to route within UAB. Okay, that's why it's called autonomous, right? So because it's other people cannot have control of how UAB allocates those internal routers. Okay, this is called the first level in the autonomous system. Okay. So AS use so-called intra-domain routing because we are under the same UAB domain, right? So, the routing protocol is just the routing stuff internally. Okay, so there are two routing protocols which we will be covering in this lecture. Okay, the first is called a RIP. Okay, RIP is not the regular meaning. Okay, it means the routing information protocol. Okay, routing information protocol. And it uses an algorithm called the distance vector, okay? And there's another protocol called OSPF. OSPF, the full name is called Open Shortest Path First, okay? So it uses another algorithm strategy called link state, okay? Distance vector and link state, okay? We will see what they are shortly, okay? But from now on, we will not call the full name, right? It's really too long, okay? So we just call RIP and OSPF, okay? Just get used to it. Okay, OSPF S means shortest path, right? Okay, and I think this is OSPF. Okay, I think there's a typo. Yeah, this is OSPF. Okay, path first. And the connections between ASs, right? So each AS is like for your UAB or your if you are living in a region, maybe the whole region is under the same autonomous system, right? With like the same HOV or something. Right? So anyway, so there's different domains, okay, under the same domain, right? So you have, how to say this? You have an autonomous system, right? This is really autonomous in each domain, okay? But when you want to route between domains, right? Even just from UAB to Auburn, for example, right? So this is inter-domain, okay? In that case, we need to run a different kind of protocols. Okay? We will see that in the next set of slides. Okay, not the current set of slides. This is called the BGP. Okay, BGP is also the name you need to memorize. Okay, usually we will not use the long name, but it's pretty obvious, right? It's called a border gateway routing, which means it's on the border, on the border of the institution. It's between the borders of different autonomous systems, or we call AS. Okay, so here you need to remember from this slide those terminology. Okay, so AS. Okay, AS is the autonomous system, which is like within the same domain. Okay, and usually the institution itself is responsible for deploying the routers and configure the hardware and determining the routing protocol. Right? You need to choose RIP or OSPF. Okay, so this AS, you need to remember it. Okay, this terminology. And then the next terminology is RIP and OSPF. Okay, these are the two so-called intra-domain routing protocols. Okay, and then the last one is called inter-domain routing protocols, which is called BGP. Okay, so these are AS, RIP, OSPF, and BGP. You need to memorize. Okay. So here's an example of AS. Right? So this is, for example, the autonomous system. Right? This is like a UAB. This is maybe Auburn. This is maybe UA. Right? So this is Alabama. And between these different institutions, they themselves forms an autonomous system. Okay, but if you want to route between them, then you need to use BGP. Okay, so here's a for example, if you look at the router here, right? So this is called the remember the border gateway, right? So this is the border gateway router because you have a link go to another domain. Okay, well this is called the interior router because it's totally serving your own, your own domain, right? Because you don't route the traffic outside. You only route traffic within your domain. Okay, so that's the concept. Okay, and within each AS we run maybe OSPF, and between we run BGP. Okay, so that's the thing that you need to memorize. Okay, then if you memorize these terminology, then when we talk about these things later, you can follow what we are talking about. Okay. So why do we need an AS? Right? Why do we need an autonomous system? Because routing algorithms are not efficient enough to execute on the entire internet topology. Okay, just like what we talked about before, right? So if you use a switch method for organizing their address, right? So and don't use the IP address, right? So which are clustered by prefix, then you cannot handle the internet. It's the same for the routing protocols. Okay, the local routing protocols like OSPF. If you want to directly apply it for the entire internet, it will not work. Okay, and when you run those routing protocols within your domain, there are not too many machines. Right? That's fine. Okay, but because each autonomous system manages their own protocols and how to route internally. Okay, then this actually other like external routers do not care about what is in your institution. Right? So this way it scales down the scale significantly, and we are able to run another BGP protocol among the different AS. Okay? So we cannot just using one routing algorithm. Okay, it's not efficient enough. We have to have the hierarchy, right? Each autonomous system. Okay. Another important reason is that different organizations may use different routing policies. Right? So maybe for you want to route like this, like OSPF, another want to use RIP, and there may be some other policies that are of concern to them. Okay, so autonomous system allows, let's say, UAB to route differently from others internally. Only when they communicate with each other, right, or with anyone else, we are using the same protocol, which is BGP. But internally, you have the flexibility to do what you want. Another important thing is that it allows organizations to hide their internal network structure, right? So if you know that some attackers want to attack UAB, but if these interior routers are belonging to UAB, right? So then when routing, you just route to the border gateway router, okay? But then internally, how the structure looks like. So the routers will handle these traffic for you, but they will not expose anything outside UAB, okay? Leak outside to outside of UAB. Right? So this is very secure. Okay, it can hide information, internal networks, and this also is good because think about we cannot just let a BGP consider also all the internal structures of the AS. Okay, because you know, BGP cannot are not efficient enough to execute our entire project. And it allows organization to choose how to route across each other. Okay, so this is actually part of the BGP. Basically, for example, right? So if you have 3 AS, right? And if you 4 AS, right? You route to here. Let's just use some illustrative form, right? So for $1, okay, and route to here for $1, okay. Right. But if you route through here, this is $10, right? And for here is $1. Maybe you will probably hey, never route through this route. Okay, so this BGP can handle this. Okay? Another possibility, even though this is also $1, but hey, here it's not trusted. Right? So this could be attacked. So I want to go through this. I will not consider this route. Okay? So this allows organizations to avoid some AS in their routing paths. Okay. So yeah, so using this two hierarchical structure allows more flexibility because each autonomous system, AS itself, has the flexibility. Right? We don't care about what outside UAV is configured. I can configure as desired. Okay, right? Like I'm an IT person in UAV. Then it's also easier to configure routes because now you basically have two hierarchies. Right? So you have a low-level stuff, but it's localized to your own institution. But you have a high level, but because those low-level details are not there. Right? So you only care about how to route between AS. Okay? So this is easier to configure routes. Okay? Again, this is the flexibility also means the more independence. Right? So you don't rely on others. Okay? And you can even say, hey, in BGP, I don't want to route through that AS. Okay? You can have that preference. And especially think about it, that could be like mobile service providers, right? They want to compete with each other. Okay, you don't want to use the other person's routing, even though physically there's a link. And so if you look at what routing is, right? So it's basically a graph. Okay, so this cylinder is not a disk. Okay, usually we also put this disk like this, right? This is a router. Okay, so you can think about how people write router. Usually it's as a cross. Right? So on the top. Okay, so what we are just saying that as long as you understand what that is. So these are routing. Okay? These are the routing. Okay? And the goal is to determine a good path through the network from the source to the destination. Right? So because these routers are how you can deliver the packets. Okay? So what is a good path? Right? So there are several criteria. Okay? Usually we want the shortest path. Right? If I can deliver the packet, let's say we use some illustrative time, right? So if I can deliver in 1 second, I don't want to deliver in 10 seconds, right? So this is an example. But again, you want a load balance, right? So for example, if, hey, this is a short path, right? So, but you think about it, if everyone is taking this short path, right? So it's like a bridge between two banks, right? So then these two routers, like on this bridge, right? So with is taking too much workload. Okay, so we want a load balance. You can take the other bridge to the other side of the bank. Right? So, and we also want lowest dollars, okay, lowest cost. This is understandable because we so. Hello, can you hear me? Yeah, I think I just lost the connection somehow. Can anyone tell me where where were I when the connection got lost?
Beginning of the slide, I guess.
Beginning of the slide. Yeah, so sorry for that. I didn't know. Okay, so yeah, I just realized its connection is lost. Okay, let me share my screen again. Yeah, so basically we want to find the best path, but we have a router graph, right? So these values on the edge can be the time, and then we want to find the shortest path time, right? Like 112 from A to F is the shortest. Okay, but sometimes we may take a longer path. Let's say this 1, 3, 5. Okay, 1, 3, 5. Okay, the reason we are doing this is because maybe E is very expensive. We don't want to route through E. Okay, route through E is fast, but it's too expensive. Right? So maybe the BGP will say, hey, don't route through E. Okay, that's too expensive. Right? So there are different considerations. Okay, so the good path doesn't always mean the quickest path, the lowest latency, etc. Okay, and in any case, we can model, the network as a graph. Right? So internally, in the same institution, usually it means the shortest path. Okay, but sometimes between AS, if these are different AS, we will consider the cost center. Okay, and so the network can be modeled as a graph, where nodes are routers or the beginning of your host sent to the router. Okay, and links, right? Those links are the edges. Okay, so these are actually physical links between two routers, right? But you can regard as edges, and there's a latency. But at least you have a like a propagation delay, and you have the bandwidth, right? How fast you can propagate onto the outgoing port. Okay. Yeah. So there's a delay and a congestion level, right? So usually, load balance will be achieved automatically in your internal institutional, interior routers, because if you have a lot of traffic go through this link, the time will grow. Okay, and then naturally the short path will reflect that. So the routing problems now looks like this, right? So let's just think about, let's say within UAB, we have so many routers, and we have N routers, right? There's a network with N nodes, okay? Right. And each node only knows its immediate neighbors, right? So you physically connect to 3, because your router has 3 ports. Yeah. B has 3 ports to A, D, and C, okay? And the cost to reach each neighbor, right? Because you can probe the other neighbor, right? How fast you can send, etc. So each router only have a localized view. Okay, B cannot see F, right? So how did this node learn the shortest path? Let's say from B to F, which one is the shortest path? Right? Apparently here it should be 2, 1, 2, right? Instead of 3, 5, okay, which is much larger. Okay. But how can we find this shortest path? Right. So this comes to our intra-domain routing protocol within NAS. So as we said, there are 2 protocols. Right? The first protocol is called RIP, okay, and it uses called a Bellman-Ford algorithm for all pair shortest path computation. Okay, it uses so-called distant vector method. So the reason is because it will maintain a vector. But each router, let's say, so just to help you memorize why this name is called a distant vector. So we will maintain a vector. Say this is A to B, like 2, okay. A to C, okay? The shortest path currently maybe it's 1 plus 3, maybe 4, okay, etc. We have a vector to every route, okay? Similar, C also has this to A, to B, to F, okay? So each one has a distant vector, and they are updated until they know which one is smallest. Right? There's a convergence because you have multiple hops. You need to communicate, and finally you know which route is shortest. Okay, so basically it's a kind of shortest path algorithm. All pair shortest path algorithm between any 2 pairs. So if you learn the algorithm design, right, in some prerequisite courses, you should know the Bellman-Ford, right? Dijkstra and the Bellman-Ford. These 2 are probably the most famous shortest path algorithm. Okay. So this Bellman-Ford all pair shortest path algorithm is run by the RIP protocol, right? And we also call it distant vector because in each router we maintain a distant vector to other routers. So the routers will periodically exchange reachability information with neighbors, right? So that you can know, hey, because your neighbor has a distant vector, the neighbors know how far they are from other neighbors, okay? Other nodes, okay? If you get the information from a neighbor and you find, hey, through that neighbor, I can reach the destination using a shorter path, I will update my vector accordingly to go through that neighbor, okay? So that's the idea. So this is the first method called RIP, okay? The second method is called the OSPF. Right? So this is called the link state method. So this is actually based on the Dijkstra algorithm. Okay, this Dijkstra algorithm for shortest path. Dijkstra algorithm is called a single source shortest path, right? From a particular point. how you do kind of breadth first, like iterative computation, right? Each time you find the next longest path, right? Because prior shorter paths are all determined, right? The next longest path must be the finalize the shorter path, okay, through the existing determined path, right? So this is the Dijkstra algorithm that is run by the OSPF, and we call this kind of algorithm called link state. Okay, we'll see why later. So logically, each network periodically floods intermediate reachability information to all routers. Okay, so here, you just communicate. This is very important. Okay, you just exchange with neighbors. Okay, but for OSPF, you will flood to all routers, which means, yeah. So just keep this in mind. I will go to the previous slide to explain. Okay, and per router local computation is needed to determine the flow route. Okay, so what does this mean? Let's go back to the previous slide. So what OSPF, what link state is doing is they only exchange distance vectors with the neighbors, okay? But maybe D knows, hey, I can go to F with a shorter path, but A previously takes this path. Now I would update this distance to maybe 1 + 1 + 2, right? Go through D, okay? But I only communicate with my neighbors. But Dijkstra is a different algorithm. It will do like a path search and build a structured path tree. Okay, and basically your information will be communicated to multiple paths to everything. Okay, so that's the difference. And another important difference is that per route local computation, right, to determine flow routes. Okay, so basically for each node you need to have the picture of the entire route. Right, it's a tree. Okay, so that's what we are talking about. Okay, so next let's look at, let me see whether we should take attendance first. Okay, I think we have good attendance now, and let's take attendance. And then we will continue with the detailed algorithms. Let me see. Okay, so let's start from the first student and skip every 2 students. Okay, Kobe, are you here, Kobe? I think does he ask for leave? Let me just check. Kobe. Oh, I see he actually asked for leave. Oh, that's fine. Yeah, let's skip to Clinton. Are you here, Clinton?
Yeah, I'm here.
Okay, thank you. Ryan, are you here? Ryan
Yeah,
Chancellor?
I'm here.
Okay. And Alex? Alex, are you here? Alex? No? I will almost call 3 times. Okay, then I will. Caleb Edwards, are you here? Caleb? No? Caleb? 3 times. Okay. Diego?
I'm here.
Okay. Rachel? Rachel, are you here?
Yeah, I'm right here.
Okay.
Can you hear me?
Yeah, I can hear you. Thank you. Michael? Michael?
Hey, I'm here.
Thank you. Daija? Daija, are you here?
Yes, sir, I'm here.
Thank you. Evan, are you here?
I'm here.
Evan Landers?
Yes, I'm here.
Okay, got it. It's not so loud, but it's fine. Okay. Francis? Francis?
I'm here.
Okay. I think she asked for leave. Sarah? Sarah, are you here?
I'm here.
Okay. Daniel? Daniel, are you here? Daniel? Daniel? No. Swap Neil?
Oh, okay.
Got it. Arvin, are you here?
Yeah, I'm here.
John, are you here?
Yes, I am here.
Emmett Smith, are you here?
I'm here.
Okay. Raina, are you here?
I'm here.
Thank you. Let's do the next list quickly. Okay, so oh, that's why I ticked the wrong list. That's fine. So let's run with sample 5 students. Okay, thank you. Siler, are you here?
I'm here.
Oh, Lawrence, are you here?
I'm here.
Thank you. Clark, are you here?
I'm here.
Thank you. Alaya, are you here?
Yes, I'm here.
Okay. Anissa, are you here?
Yes, I'm here.
Okay, thank you. So we take up quite some time, so we'll just do it here. Okay, so next let's look at the distant vector routing. Okay, so basically, if you remember, distant vector is for the Bellman-Ford algorithm and for the RIP protocol. Okay, so here why we call it distant vector, or what is a distant vector, right? So distant vector, as we just illustrated, is each router you have a table, right? So it's like a vector because you keep the shortest distance to every other. Okay. Oh, I see Caleb is here, so just to see the chat. I think it's the other. Yeah, if I missed you further, just let me know so that we just send me email. Okay, I will fix that. Okay, otherwise, it will take too much time. But so yeah, so basically we have a vector, right? The first item in the vector is say what's your current router's shortest distance to the first router. Okay, what's the second item is what's the shortest distance to the second router. Okay, the third is what's the shortest distance to the third router. Okay. So the idea is to exchange vectors among neighbors, okay, to learn about the lowest cost path, right? So basically, you only get to know a lower cost path from your neighbor. Okay? You don't directly communicate with any router that is not directly connected. Okay? So this is the idea. And here is an example of what is this? Anyway, so here we don't have a we have an example of the DV. DV is this map table. Okay, at a particular node. Let's say here we are at routers node C. Okay, of course C to C itself doesn't make sense, so we have no entry for C. Then this vector only has these values. Okay, which is a distance to A, B, D, E, F. Okay. Currently we are saying that hey, your shortest path to A from C to A. Okay, because your current node is C. C to A is 7. C to B is 1, C to D is 2, C to E is 5, C to F is 1. Okay? That's what it means. But initially, you only have information of your immediate neighbors. Right? Let's say that you install a new router into the network, right? And you connect the port with the directly connected routers. Of course, you know how far you're away from the other routers, right? But that's the only information you have. Okay? For the other destinations, right, you basically you don't know how far you are from them. Initialize them as infinity. Okay? But eventually this table will be filled. Absolutely. Because you keep talking to your neighbors. And your neighbor may know these shorter passes. Okay? So that's the idea. And this distant vector routing is adopted by the RIP protocol. Okay? P itself means protocol, but we just call it RIP protocol. Okay? So here's the algorithm workflow. So it's a looping of these operations, right? The first step is wait for change in the local link cost, right? Because maybe you already converge, you already currently know the short path to other routers. Okay, so then there's no need to keep communicating. But if you find, hey, there's a change in your local link cost, right? Then you need to say, hey, for example, previously between A and B, it takes, let's say, 1 second. Right now, because of congestion, it takes 10 seconds, right? You need to propagate that. All the other people who think you are routing from A to B with 1 second should be updated, right? Because this is slower now. Okay, so maybe they should take another route. So if there's a change in your local link, right? So you first wait, you don't do anything because there's no change. Right? But as long as you have a change in your local link, which means your adjacent links, okay? Or you get a message from neighbors, because neighbor may detect this change and send some message to you. Then you will be like awakened up to propagate the information to others. Okay. Right. So if there's any change in the network, right? So this will, or you receive any message from the neighbors. Okay? Then you have to recompute the distance table because the distance changed. Right? Previously, you probably are routing through maybe that neighbor, right? But that neighbor now, the path no longer takes 1 second. It may take 10 seconds. Now you need to recompute. Maybe you take another pass after 2 seconds. It's better. Okay? So if the least cost path to any destination has changed, then you need to notify neighbors. Okay. So here again, we want to minimize the message. Okay. Because if your least path is not changed, right? So then anything routing through you, right? Your neighbor routes through you, they can still rely on you. Okay. Because maybe we do have some change, but that change is not affecting all my routes from my side, right? Then any path routes through you still reach the destination using an old path. Okay? You don't need to trigger other people, other routers to wake up and do the propagation. Okay? So only when at least for some destination, right? Your cost now change. Basically your distance vector, some entry change. Then you need to communicate with your neighbors to broadcast this information. Okay? Because otherwise the neighbor may be routing through this entry, which may be wrong. Okay? So, and then you will repeat. After it's converged, you just wait. Okay? And when you receive triggered by others, or you detect your adjacent link has some change in time, then you will basically do this computation again. So how do we do the computation? We will see that in the next slide. Okay. So any questions so far? Just want to give you an intuition first. Okay, so now let's take a look at how the algorithm will run. Okay, so let's just consider this toy router structure, right? So the network routers, A, B, C, and D, and the weights currently are like this. You can think about latency, how long it takes to send, okay? Or the bandwidth. Usually it should be the bandwidth, right? How fast you can send, okay? And so initially what you will do is this, right? So if you're, for example, for this router, okay, let's consider node A, okay, this A, right? So because your port is connected to B and C, you immediately know, your distance B and your C is like this, right? So you directly get the cost rate, okay? But now you don't have a direct port connected with D, right? D is connecting to you through B and C. So initially you don't know how far away you are from D, so you initialize as infinity. Actually, additionally, besides this vector, okay, this vector also associated with this. Right? So where's the next, router you should send on your shortest path, right? Least costly path. Okay. Here because you route to B, right? The next hop is also B. Right? So then you say next is B. Okay. Right? So, but in some cases, I see a chat. Just a minute. Oh, Daniel, let me see. Okay, so attendance. Yeah, next is just to send me email, okay, because okay, so I will put you back. Let me find my mouse. Now, if you want, just send me email from now on. Okay, so I will fix it. So, so for multi-hops, right? So for example, if you have, no, this is not the short path. Right? This is the short path. Okay, right? 2 + 1 + 1 = 4. Okay, for this short path, right? So you can say A go to D. Okay, now from A to D. But if it converges, it should be 4. Okay, because it's 2 + 1 + 1 = 4. But the next should be B. Right? So you first go to B and then go to D. Go to D. Okay, so this is B. This is our final target. Right? So that's what the next means. So initially, if you set A like this, set B like this, right? B is connected everywhere. So basically, you get some initial cost. And then next you will loop through the operation we just described, right? So how do we interpret this? Right? So this is super long. Okay, this is super long. But let's just make sense of the operation. Okay. Firstly, if there's an update of distance, right, and then the neighbor will notify you, okay? Or if you yourself have a distance, okay? Then you need to send a updated value to neighbor. Okay? But before that, you will see, hey, for example, now it's received from B, right? V. Okay. Let's say A is receiving some vector from B because B this value changed. Then you need to tell A, hey, I have value changed. Maybe you want to change. Okay. And because of this reason, A will see, hey, if I route through U, right, from A to V and then V to Y, because the actual destination. Okay. Well, it will be shorter. Okay. If it's shorter, right, so we will take a mean. Okay, we'll take a mean. If it's a shorter, then we originally I'm routing through the next with C, then I should route through B. Right. Another case is it's my next originally is from B. Okay, so it's already routing through U, right, through V. Okay. And then I just do the addition, right? So A to B and then B to D. Right? So really because maybe now your B to D's value is changed. Right? So then but this value I can probe myself. Okay. So I just do the addition. Okay. So there are two cases. The first case is I route through U to the, but now B is changed. Maybe this 3 goes to 5. But I can probe this part, right? But this path to the destination may change. You need to tell you. Okay. And then you just add an update because this thing may be changed from B. Okay. Another case is the origin you route through here, but you B tells you, hey, route through me is shorter. Then you will do this. Okay. Any questions? This is intuition. Okay, this algorithm to come. Let's look at how this thing runs. Okay. So firstly, for example, this is the initial table that we see in the previous slide. Now you think about the C, right? C, let's say, will send messages to A because of some update, and the C is sending this data. Okay. C to A is 7, C to B is 1, C to D is 1. Okay. Now what happens is A originally cannot reach D, right? But A can reach C. Right? So let me. A can reach C in a cost of 7. Right? But then C send a message to you, tell you that C itself can reach D, right, in cost 1. Right? So then you can reach D in cost 8. Right? So then you should update. Okay. So this becomes 8. Right? Because originally you have infinity, now it's 8. Of course you update it. And you route through C. A through C to D. Okay. So that's what we are doing here. And then, for example, then you receive some message from B, right? And B gives you this distance vector, okay? And then what you find is B tells you, hey, I can reach D across 3. But then when this message comes to A, what A will find is A knows this crosses 2. It's adjacent. So A knows that its distance B, it's adjacent, so it can always keep track of this value, is 2. Now A knows its distance to B is 2, but B again tells you its distance to D is 3. Right? So A to D can route through B is 5. Okay. If you remember previously, we said this is 8. Right? Okay. 5 is shorter. Okay. And let me see. Here we are talking about C first. Okay, sorry. Let's first finish up D. Okay. So for D, as we said, originally it's a value of 8, but we find a shorter path, 2 plus 3, 5. So we update this to B. Okay. And you will previously route through C. Right? Now you will route through B. Okay. So yeah, let's look at the C. C will also update in this case because previously your distance to C. Let me change the code. Okay. Your distance to C is 7. Okay. But 7 is crazy, right? So this is this value is too big. It's not worth it. Okay. Maybe this link is 0 or not. It doesn't matter because you can go here. It's faster. This is which it tells. But A knows that originally go to C is 7. But now B tells you, hey, go from me to C is 1. Okay? But A to B is 2, B to C is 1. So then we update to 3. Okay? Any questions here? Yeah, something like this. And we will do all the updates, just like we described. Because, you know, A will send broadcast its destination to B, broadcast to ACD, etc. Okay. And after all the update, we will have these. Right. You can see the cost is reduced. Okay. And we will repeat doing this. Okay. Until the nothing changes. Right. By that time, we know that everyone terminates. Everyone knows the short path to everyone else. Okay. And this is stable status until when, let's say, something changes. Let's say this 7 goes down to 1. Okay? Then you do more update. Right? Previously, you say this is 3, so I go to C is 3. But now, if I detect this becomes 1, I should just go to C directly. Okay? So until something changes, then you will be triggered to do this kind of computation again. Any question here? I hope this is easier to understand for you. Okay, next let's look at this solution, whether there are some issues, right? So some weaknesses with the solution. So firstly, let's take a look at here, okay. Node B and node C, okay? Right. So right now, we only have 3 routers. What if, let's say, we change this cost, right? So suddenly it will become fast, okay? Maybe congestion is gone and it becomes 1, right? So the time to travel is reduced, okay? So what we want to do is this, okay? Previously, we know that node B route to A is 4. Now it becomes 1. Once you have this update, so what you need to do is B detects adjacent port has a faster speed. It will send the distance vector like this, okay, to neighbors like A and C. Right. Let's look at C. C will receive this distance vector from B, okay, from B. So you get it? But C previously have a value 5 to it. Okay? If you look at C previously, this is 50. This is 1 plus 4. 1. Now you tell C, hey, right? You know, C previously is already routing through B. But C is previously already routing through B. Now you are still routing through B, so we will go this path. Okay, we change this. Previously, it's a 1, right? C is adjacent link, 1 plus 4. Now this 4 goes to 1, essentially, goes to 1. Then this becomes 1 plus 1, okay, becomes 2. Right? So we will update this as 2, but we are still routing through B. Okay. And then because C, you know, C has its disconnector update. Now it needs to broadcast this information to its neighbors. Okay. So one neighbor is, for example, B again. So it will send it back to B. Okay. But when you send it back to B, since we're terminated, because you know B is already 1, 1. Right? These 2 will not play a part in reducing password. Okay, so it terminates. So what does that mean? That means, you know, just a ping pong, one operation. Okay. Right, you propagate this good information from 4 to 1 already. Right, you find the short path immediately. So this is called good news travels fast. Okay, good news travels fast. But there's a reverse situation. Right, so what if you have bad news? Right? Originally it's super fast, like 4 seconds to travel, but now it becomes 60 seconds. Again, this time doesn't make sense, right? So because I'm using second, maybe it's a millisecond, no. But anyway, it's just for illustration, okay? So if this happens, right? Again, here we are talking about transmission time. Okay? If you think about the bandwidth, it's a kind of reverse, right? If your bandwidth is high, then your transmission short. Okay? So we are just for illustrating this. Okay? Then we can show, because we are running out of time, we can show this kind of ping pong operation, right? You go C, go to 7, go to 8, go to 9, and something, all the way go to 16. Okay? So this will go on forever. So bad news will travel slow. But we will do the analysis of this in the next class. Okay. Because the time is up, so I will just stop here. Okay. Any questions regarding what we covered so far? I will be here for 2 minutes. Because this thing will take some time to analysis. Okay, so I will send this slide to Canvas, and I will also upload the video to YouTube. Okay, and you will get an announcement about it. Any other questions? If not, I will just end this class. I see one. Okay, thank you. I do not see any question. Okay, in that case, have a nice day. Okay, I will update Canvas so that all the necessary files. Okay, bye.